Okay, yes.
Very good.
After all the troubles, so good afternoon, everybody. So thank you, Jerry, for the very nice introduction. So my name is Peter Ngene. I'm from Utrecht University here in the Netherlands. So in this SACS online lecture, I'll just be showing you some of our efforts to use X-ray Raman scattering to understand some of the interface-induced effects we do see in our metal-hydride nanocomposite material, which are basically material for energy conversion and storage. This is just the overview of the talk. I'm going to give you some small motivation about why we care about metal-hydride, why my work has been on this material, and then I will not go into two specific examples on our X-rays based studies on the nanocomposite for reversible hydrogen storage, and then I'll also give some example on the use of this same material as ionic conductors for batteries, and some concluding remarks. So if you go right away, so the motivation of my work is basically to use to develop novel materials or new materials for energy conversion and storage, energy materials I call them. I think we all might know, or we should know, that there is this transition, there's this energy transition, basically going from the fossil fuels to energy based on renewables such as solar and wind. And basically the problem with this is their intermittent nature. So we have to develop means, materials and technologies to be able to actually store this energy when they're available, so that we can actually use the electricity when it's not available and we need them. So I think there are many ways to do this, and one of the really robust way of doing this is actually electrochemical energy storage in batteries. So we can use high energy density battery. Such kind of battery actually can already we have electric vehicles where we can use such kind of batteries actually to drive cars and therefore mobility. So we don't really need to care about gasoline again. So this is actually one of the dreams. We're going to get them. And of course, we can as well combine these high energy density batteries with solar panels at home, and then we should be able to be completely grid free if that works. So another way is also electrochemical conversion. So in this case, we can use electricity to drive a lot of chemical reactions. In this case, like nitrogen fixation, where we can make ammonia, but we can also do CO2 conversion together with water, where we can generate a lot of the feedstock that are being used for today's chemical processes. And we can also make hydrogen in the process as well, where we can use this hydrogen to drive car in hydrogen fuel cell vehicles, and also to power our industries. So basically, this is just the way I do. So this is my approach to my research all this while, developing new materials that will enable us to do this kind of things. And so which are the material? Of course, battery material, as I already mentioned that. So we have also catalysis. So we need catalysts to be able to do all this kind of electrochemical conversion. And also we need hydrogen storage material, because as we're going to see, hydrogen, it's a gas, and because of its light density, then we need a way to contain it. So in that case, we're working on ammonia-based hydrogen carrier and other hydrogen carriers, such as liquid organic hydrogen carriers, and then metal hydrides. Metal hydrides. Most of the elements do react with hydrogen to form different kind of hydrides. So except with few exceptions, which you can see here in the yellow, that don't do that. But most of this material actually can form hydrides. They can react with hydrogen to form hydrides. And so these hydrides can be classified according to the type of chemical bonding, the bonding character between the metal or any other elements and this. So we're looking at basically the metal-based one. So we have the ionic hydrides. In this case, you have just ionic bond between hydrogen and metal. As you can see, something like sodium hydride, lithium hydride, and potassium hydride. I'm going to show some examples in this case. So we also have what we call the metallic hydrides. These are basically transition metals and also rare earth metals, where actually hydrogen, can dissolve in this material. It's often non-stoichiometric. So in that case, some can be stoichiometric, but often non-stoichiometric. And we have what we call the covalent or polymeric hydride, something like alane, aluminum hydride, which this is not thermodynamically unstable. We also have a diborane, and this complex hydride, so we call complex hydride, which I gave some examples here. These are very interesting ones. So these ones I underlined. These are actually the ones I'm going to show you later on. So this is a situation whereby you have, a complex anion like these ones, that is ionically bonded to a metal. So that's why it's called complex hydride. Now, why do I care about hydride? So this example of this complex hydride, why do I care about hydride? So the metal hydrides actually, I think they gain popularity because of the ability to store large amounts of hydrogen in their structure. As I've shown here, basically this is lithium borohydride that if you heat it up, it can decompose to give lithium hydride and boron plus about 14% hydrogen. So people were interested in this kind of material to reversibly store hydrogen because it's better to store hydrogen in this way than actually storing hydrogen in tanks, as we're going to see. So that was the initial interest in this type of material. But nowadays, metal hydride they became what I call multifunctional energy material, because apart from hydrogen storage, reversible hydrogen storage, they are now being used for thermal energy storage, where you make use of the difference in the enthalpy of hydrogenation and dehydrogenation of certain metal hydride, actually to reversibly store heat. And then in just about 10 years, or roughly more than 10 years right now, they also attracted a lot of attention as ionic conductors, not only lithium and sodium, but also even magnesium and calcium ion conductors for different kind of batteries. And also, again, it's hydride ion conductors, where the negatively charged hydrogen ion in certain material actually are very, very mobile. You can use this actually to do a lot of electrochemical conversion. And actually, they are one of the most fascinating superconducting material that are being reported, in recent time. So these are multifunctional energy material. Also, you can use the fact that when metals absorb hydrogen, so there's a reversible change in the optical property of this metal. You can actually use this to realize a lot of hydrogen sensors that can be used for all kinds of applications that I don't have time to discuss. So during my postdoc, I work on this kind of thing. Just what you can see here is just the reversible change in color of this yttrium hydride upon exposure for different amounts of hydrogen, actually. And which means you can actually use this to actually make what we call, hydrogen detector, optical-based hydrogen detector that just changes color by the fact that there's hydrogen available there. So these materials are actually a very interesting class of material. And recent times also catalysis, we are doing catalysis with this kind of material, where the fact that, okay, they release atomic hydrogen during decomposition, that you can actually use this effect, actually do all kinds of catalysis, olefin hydrogenation, CO2 hydrogenation, and I'm going to show you a little bit example of what we do in ammonia. So other things, apart from catalysis, luminescence, I talk about sensing, and also nuclear shielding. So these materials actually, you can really see that they are interesting for a lot of application. So now what I want to just do is to just give you a very quick overview of the work that we have done previously on this material, especially in terms of hydrogen storage. So why do we care about hydrogen storage? I think I just mentioned this is a cartoon that you can see here, because of the fact that, of course, hydrogen in terms of its energy density per gram or per kilogram, you can see it's way more than gasoline. However, because of its low density, what you see is that in terms of the volumetric energy density is quite low. So if you want to store hydrogen, if you need to use hydrogen to drive a car, if you don't do anything, actually the size of the tank or the storage tank is going to be much higher than actually the dimensions of your car. So basically we have to do something. Of course, we can liquefy the hydrogen, but you have to go to very low temperature to do this. I think this is about minus 253 degrees centigrade, I think, if I'm correct, but it's within that value. And you have to try to keep it there. You can also go to high pressure gaseous hydrogen. And in that case, of course, then you need very heavy tanks, which also bring down so much the gravimetric energy density of hydrogen when you put them in such kind of heavy tank. We can do desorption, but another very interesting idea is a solid state storage in hydride, metal-hydride. It's a result to more compact and safer way of handling hydrogen. And about 20 years ago, there was a lot of work on really looking at new materials that can store hydrogen that can reversibly store hydrogen. And so this is just some of the materials, that have been used. These are some of the metal hydrides that, of course, if you hydrogenate the metal, and then they can give you metal hydride, and if you heat them to high temperature, then this hydride will decompose. So you can actually use the hydrogen to drive your car. And when it's done, you can take back the metal to the filling station, and they put high pressure of hydrogen there. So there's a lot of research into this. And already what you can see here, that's okay, this is the DOE target for the type of material that can be used. So you need to store about 5.5% hydrogen at this moderate condition, about 100 to 150 degrees centigrade. However, if you look at most of the metal hydride, you see is either that they store very small amount of hydrogen at this, temperature window, or that's the ones that contain so high amount of hydrogen, like the sodium borohydride, magnesium borohydride, lithium borohydride. This is a very interesting one because it has about 18% hydrogen if you go full decomposition. However, you can see that the temperature window at which it can release the hydrogen is quite high, so then it's not doable. We cannot use this. Also, all these ones. And also, if you look at all these other ones, so like Alane, which is a very interesting one, you see that it's thermodynamically unstable. So, and also the same thing with lithium alanate. So, nature doesn't give us free lunch, so we always have to find a way to use what nature has provided to get the lunch, right? So, how can we now begin to shift all these things, to play with thermodynamics, to be able to shift all this attractive material to be in this, temperature window? And also another problem with this material is that when you also have released hydrogen from them, it might be difficult actually to take the hydrogen back because the reversibility kinetics is quite poor. So, this is so our approach then was just to make what we call to do nano-confinement. So why do we want to do nano-confinement? First of all, what is it? So we have a metal hydride and we have a scaffold material. In this case, something like carbon. So this is just, a cartoon. And then we can put this metal hydride in this small carbon, the porous carbon. So we need, a scaffold that is quite porous, so we can actually put all this metal hydride in there. So it can be carbon, it can be metal organic framework or silica. But for this metal hydride, because they are very reactive with MOFs and metal oxide, as you're going to see, we started with carbon. So why do we want to do this? There are so many benefits of doing this. So the idea is that when we do that, you can actually reduce the particle size. We do know that when the particle size is small, then you can enhance, a mass transport, and the kinetics will be highly enhanced. Another thing is also we can play with the fact that there could be hydride support interaction. So there could be some kind of interaction that could be beneficial towards, changing or destabilizing or stabilizing this hydride because of this interaction. And then also you can restrict phase segregation. Why do I talk about phase segregation? So for example, if you have lithium borohydride, which is quite attractive, if you heat it up to high temperature, what happens? So it goes into lithium hydride plus boron and plus hydrogen. Now, we all know that this is solid material. This is also solid. And then, so we want to do the reverse reaction. You want to this boron and the lithium hydride to combine, and then also with hydrogen to form back a lithium borohydride. And because of the phase segregation, this often doesn't happen. It doesn't happen because of the fact that, okay, the diffusion, the mass transport for the solid states are quite low, so it doesn't happen. So if you're able to confine them inside these very small pores, then that means that both the boron in this case and the lithium hydride will be close to each other. That when you want to do the reverse reaction, it is easy for them to find each other and then to form back again lithium borohydride. So that's one of the things. Another thing is also what we call clamping of physical constraints. If you go from metal to metal hydride, because this hydride has to go into the structure of the metal, there's always a huge phase, huge expansion of your material. And then if you now suppress this expansion, you can actually use that to actually modify the thermodynamics of hydrogen absorption and desorption in this. So by just restricting this a volume change, you'll be able to do this. So how do we do this? Very simple. We just mix. So this is in this case carbon, and this is our bulk metal hydride. And then if you just infiltrate, either by heating or doing what we call impregnation, then you will now have all these metal hydrides dissolve, or confined in this small carbon, porosity of carbon. Here I just want to give you just overview to show that actually this works, so you don't have to go into detail. We start with this lithium borohydride here. So this is the bulk lithium borohydride. So what do we do here? So you have your sample, and then you heat it up, and then basically you monitor the rate at the rate at which the hydrogen flows during the heating. And you can see that if you start with the bulk material here, that you need to go to really almost above 400 degrees centigrade, almost 500 degrees centigrade for you to get your hydrogen out. But if you put this inside this carbon, if you nanostructure it and confine it in this carbon, what you see is already at much lower temperature, you can actually release the hydrogen. And then we have much higher amount of hydrogen compared even to the bulk. But we're going to come back to this. The same thing we do see for sodium borohydride, that by the way has a very large amount of hydrogen. You see also we can see the same thing here. And if you go for lithium hydride, just pure lithium hydride, if you want to just get hydrogen from lithium hydride, you need to go to above 600 degrees centigrade. However, if we just confine it in carbon, you already see that even around 100 degrees centigrade, you can begin to release hydrogen. So this is really, so this nano confinement makes great impact on the properties of this material. And what about reversibility? So what do I mean by reversibility? The ability to take hydrogen after you have decomposed the material. We do see that if you have the bulk sodium borohydride, if you don't do anything, after it decomposes, here you heat it up under hydrogen pressure. You want to monitor how much hydrogen is absorbed. In this case, by reaction to make hydride. And then you can see that the sodium borohydride doesn't work. The same thing as also lithium borohydride, even when they are supported on just pure graphite. Now, if you do the nanocomposite, if you just put them inside the scaffold pores, which are very small pores, about between, I think, depending on the scaffold, can be from 2 to 10 nanometer, you do see that actually both sodium borohydride and lithium borohydride that has been decomposed can also reabsorb hydrogen. So this is quite interesting. But then also another interesting thing is also that actually ammonia, I think I mentioned before, is like an hydrogen and energy carrier. So we can reversibly use ammonia to release hydrogen, and we can just react nitrogen, which is abundant in the air, with hydrogen to make ammonia. So many organizations and companies are looking at ammonia as a future energy carrier because it's easier to handle than hydrogen. We can easily liquefy it, we can transport it across countries and continents. But of course, you need to find a way to decompose this ammonia, actually to make hydrogen and nitrogen from it. And this is just one of the work we did in time past to show that actually these metal hydrides, actually, so here we're looking at sodium hydride that we confine inside graphene nanoplates, which is just a nanoplatelet graphite. And what we can see is that when we compare this material, you can see that actually, so this is the amount of ammonia that is converted as a function of temperature. Now, the classical catalyst that is used to do this is ruthenium. So ruthenium is a classical catalyst, but we can see that when we add this metal hydride, sodium imide, potassium imide, we do see that actually the activity, our ability to crack ammonia at moderate temperature is much, much higher. So this metal hydride is not only for hydrogen storage, but also they serve as a catalyst. And another wonderful one is actually that can we now even make ammonia? Actually, and this is a serendipity kind of experiment that actually show that if we are able to put potassium hydride inside certain type of carbon here, we put it inside the pores. Actually, so potassium hydride actually can convert nitrogen and hydrogen back to ammonia at moderate temperature, even better the ruthenium, which is the classical catalyst for making ammonia. And this makes it at much lower temperature. So, which means that we have the first a transition metal-free catalyst that can actually make ammonia at moderate temperature. And these materials are quite, you can see here, they're very, very stable. We can go up to 70 hours and we have stable, ammonia conversion. So these materials are very interesting. And that's actually what I want to convince you to do, to convince you about. So the thing is that what is the origin of all this wonderful change in the properties, both in especially kinetics, that we see when we have this, when we confine this material? Is it just nanosizing? I don't think so, because if you just ball mill this material, you don't have this kind of profound effects on kinetics. So we are looking at, is it now hydride support interaction, so the interaction between this and the support, or is it change in the decomposition pathway of this material? Why do we talk about change in the decomposition pathway, which is actually changing the thermodynamics? Is because if we hit bulk like lithium borohydride, it goes into lithium hydride plus boron and hydrogen, releasing this reaction will give you about 13.58% hydrogen. However, if you put this lithium borohydride inside this small nanopores, what we do see, as you can see here, this is a one-step decomposition. And this one-step decomposition gives rise to 18 wet percent hydrogen, which means that we have straight decomposition of this material into metallic lithium, boron, and hydrogen. And of course, there was a lot of work during that time. And so we wanted to really see, can we understand what is going on with this material? And that is where we started with X-ray Raman scattering. And of course, why somebody will ask why X-ray Raman scattering is very difficult. Why didn't you use other technique? The fact is that most of this material, they are quite amorphous when you make them. If you just nano-confine them, they have no long-range crystallinity, so you don't see what you cannot just use XRD to look at the structure. And of course, NMR, NMR is very, we did a lot of NMR work, but then with the NMR, actually, you cannot do in-situ measurement really to be able to look at the phases you are forming during the decomposition of this material. So that is why we looked at, okay, which other technique actually we can use. And because these materials are very light, then it was difficult to use even soft sacks to do this. So that's how we now went for NMR. Jerry, I don't know if it's the right time to take a break, or should I just maybe finish the talk on the XRS result we have for this?
Why don't we take just a quick break here? Matthew, you had a question?
Yeah, I was thinking in terms of practical use, for instance, for cars. One of the issues with electric cars is that they just take so long to charge. You have to wait an hour to get a reasonable amount of charge. And I see in the lower left-hand graph that you're showing now that if you use this lithium borohydride composite, it would still take you an hour to charge. That is in terms of reintroducing hydrogen. So yes. I wonder if what the prospects are for getting that down to minutes.
I think it's a very good observation. But of course, we can also play a trick that we also do for batteries, because also, I work on batteries. So if you just say, okay, well, I just want to go to 50% of my value, I don't want to do the complete charging. So if you just stay at this point to this point, you see that actually you see that before half an hour, you'll be able to charge it. So you can imagine if you have a material that has, for example, 18% hydrogen. If you just charge even half of it in less than an hour, then you're already way better than today's battery. Of course, I'm not saying that these materials are there, but it's just in terms of practicality, it's just a matter of finding the right material that has more amount of hydrogen, and you can also play with the kinetics. Another thing I did not show here is because it's going to be too much, that this same sample right now, we can play a trick, and we did it in some of the publication. So we can add a catalyst in here, something like nickel. Very small amount of it, just even 1 weight percent, you put the catalyst inside the pores, very close to the compound. And what happens is that you can also really, increase the rate of this hydrogen uptake even by half. You can increase
Okay,
it by,
so that might get you to 15 minutes to get enough charge to get you moving again.
Yes.
Gentlemen, I think we're doing a little bit of a tangent, and I'm worried about time. So
Okay.
I'll suggest we hold this for informal discussion afterwards, and we let Peter continue.
Okay.
All
Good.
right, very good.
Now we wanted to understand what was going on with this sample. So then that was when I got introduced to X-ray Raman Scattering, thanks to Frank de Groot, who was also my colleague that time. And I still work together with him, we collaborate. And basically, I think there have been a lot of talk on X-ray Raman Scattering, but what it's different from X-ray absorption spectroscopy in the sense that, okay, with X-ray absorption spectroscopy, you come with, photon in and photon out. For X-ray Raman scattering, it's almost the same thing, but this case, what we are just really probing here is you can come with high energy that is much higher than the binding energy of the material you're interested in. And then basically you have your detector that is fixed at certain energy. And what you really measure is just the difference between the incoming energy and the outgoing energy. And once this difference is, which I try to put here, once the difference is equal to the binding energy of your sample, then you're going to get a signal. And this also has an angular dependence, which, it is a bit more complicated, but it has also an angular dependence. And with this, you can actually even get more of the properties of the material by looking at the angular dependence of your signal. Yeah. And why is this very interesting for us? Of course, like also X-ray, all the X-ray absorption spectroscopy is element specific. In this case, because we can use high X-ray, of course, if you have this light element like lithium, want to look at lithium, want to look at boron, you need to go to use soft X-ray to do that, because you need to go to low energy, which will correspond to the K1 of your element. But then you need then to have high vacuum. You need to have very thin sample, and for hydride, they don't survive under vacuum. They just decompose completely. So, but with this X-ray Raman scattering, there's no need for that. So we can get, also bulk and thin samples. Both bulk and thin samples are quite good, and we can also do in situ, because we can now flow gases in that. And also where this is, we can also even go to lower concentration. In this case, we can also go to low concentration. Of course, low is quite relative. So, so the first experiment that we did was with Peter Miedema, who was my colleague then. So we took this sample to SSRL, beamline 6. And so basically we started looking at, the idea is to look at, okay, what happens? So what happens when we decompose this material? So we want to investigate the evolution of phase upon heating. So we made this reactor that took some years to make them, so we are able to flow gas through this, and then we can heat our sample at the same time. So it wasn't a very successful experiment, but of course there are a lot of complications when you do something the first time. So we started with our bulk material. So in this case is the bulk powder. So this is the lithium KH. So, and this is how it looks like at room temperature. If we heat the sample up, you begin to see another peak here appearing. And then we go to, if we cool it down again at room temperature, we do see this same peak again. So we couldn't go to higher temperature that time, because then there's a lot of complication, there's melting, and so it wasn't successful. Okay. Now, if you look also at the boron edge, we do see the same thing, that of course, when you begin to heat, you begin to see this, additional features that becomes more pronounced when you're heating the sample at certain temperature. So here, if we come back to the nanocomposite, what do we see? When we compare the nanocomposite that we made, so this is the room temperature, you already begin to see that this signature, which is here after heating, is already present at this 194 EV. That's it's already present, even without doing anything. And immediately we heat the sample just 175 degrees centigrade, you see that it's completely this. So all the bulk-like behavior is gone. We only have this material. So which means that already our sample, if this is the decomposition product, we're going to come back to, that already our sample is already decomposed. So when we cool it down at room temperature, we do see the same kind of thing again, that this remains, so which So the idea, okay, what is going on here? What is this particular peak around 194 eV? If you look also at the boron, the lithium edge, I mean to say the lithium here, you see also the same thing happening here. So at room temperature, we have this, and then already when we hit our sample, you see that actually it changes completely. So of course, the signal to noise ratio was not good at that time. It has improved much better now, but at least just it's good to show this data, also to show the journey we do in science, right? So you can see that this is really. So we wanted to figure out what exactly is this peak at this 194 EV. And so we did fingerprinting them, because also even the calculation that time was not well developed. So we did fingerprinting. We started with all kind of different, boron-based compound for the boron KH, and also different, looking at boron base, because the boron spectra was much better compared to the lithium. So what we do see here, these are different, reference compound, including sodium borohydride, and these are the compounds that we can think, okay, it could be part of the composition product, like this particular compound and boron. And if we look at all these things, we do see that actually this, our peak, which appears in this material, is actually more of the oxidic boron peak. So you can see here B2O3 or also LiBO2. So the and then the conclusion that time is that that we have some kind of boron oxygen-like bond, which means that maybe our samples are decomposing upon our samples are decomposing. So also we look at the lithium KH, not very good data, but the summary of this is that we thought, okay, that we have this BO bond. So the sample has oxidized, even though we try as much as possible to prevent oxidation. And of course, this is what most of the referees said during that time, that, okay, you guys are, but we know it was not completely BO bond, because why? Is that also our sample, we can partially hydrogenate the sample. So we do know if you have this lithium borate, then your sample will not be able to absorb hydrogen again, because this material is just a thermodynamic sink. But one interesting thing that actually we saw from this experiment is that if we look at the carbon edge, so this is the carbon edge of our material as prepared. So when we heat it up and we remove all the hydrogen, so dehydrogenation, we do see some change here. And when we do rehydrogenation, so we put back hydrogen, so we form back lithium borohydride, these things seems to disappear. And we didn't know why. It took us a long time to do to figure out what was happening. But then I came back to the fact that we also had some kind of, then I looked at the XRD. Of course, the carbon itself, you cannot see the active material, which is lithium borohydride, but actually the carbon, because it's graphite carbon, it has some peak around this 2 theta, 30 degree 2 theta. And then we look at this again to really figure out what is going on here, because we do see that something to be changing with the carbon. And what we did see here, if you look at the as prepared sample, and then this is after the nanocomposite, after dehydrogenation, we remove the hydrogen, you see there is this peak has shifted backward towards lower 2 theta degree. And when we do rehydrogenation, we do see that it shifted back. So this thing that we observe with X-ray Raman scattering is also, we can see that also when we do from this. And with that, we actually look also at NMR, and we do see some things. But what we learned from this is that actually what we did see is that for the fact that this is reversible, this suggests that the lithium is intercalated in the graphene layers when we dissolve this material. And so, which means that this kind of reaction is going on, because we do know that the lithium can intercalate. So, and because of the fact that the carbon, this lithium borohydride, is very close to the carbon, then you form LiC6, which is already known in battery that you can intercalate this. And then that is the only way you can actually get 18% hydrogen, which we saw in this other material. So this is something that actually we learned from doing this X-ray Raman scattering. Even though we thought then it wasn't really what we wanted, because we didn't see evolution of phases. If you just heat it up, you see that the phase changed immediately. So we couldn't see, okay, what was the evolution of the phases. but using this, we're able to see this. And then we now look, so this actually why we now know that we can do destabilization of our lithium borohydride into this thing to actually get very high amount of hydrogen. But also, we're also worried because exactly, it's good to show this. It's also good to show some kind of experiment that didn't work out, right? So we do see that also that if we just, if we just measure, if you just do X-rays, so this is the first, and then there's the second, and this is the third. Without heating, we also do see that this peak, which we attributed to the decomposition product, is also increasing with time, which basically, show, okay, maybe it's instability, or is it being damaged, or is it oxidation? Because we do know that this peak also can correspond to oxidic boron species. So, and because of all this, that is also why, we were very careful with these first two papers that we published in PCCP, because we did see this. So I think that is maybe the first part of this talk, what we can learn from using X-ray Raman scattering to look at this nano-confined material, to look at why, they behave differently. So I think it might be a good time to take another break, or we can just continue with the battery part.
Why don't we have just one brief question thread? Greg, you had some questions about isotope effects and neutrons and whatnot.
Yeah, and I sort of, by listening, I sort of figured it out, but I'll put it out there. Okay. One question, first question is, are isotope effect studies useful? I looking at some of your earlier kinetics, and related to that is one issue, I've been involved with neutron studies. So this nicely complements the neutron studies, where the neutrons focus on the hydrogen, and it's not easy to change from hydrogen to deuterium because that messes up the neutron signals. And this is nice that you can look at the non-hydrogen element. So this is a nice study that complements it. I'm a theorist. I don't care. The more signals, the better. But you can comment on some of those.
Okay, thank you for the suggestion. I think we did a lot of quasi-elastic neutron scattering measurements before, and I plan to still do more. But it's been hard to get beam time, especially at PSI. So, so we did already quasi-elastic neutron scattering studies on this material before now.
It'd be nice, to compare. I'm familiar with the aminoboranes, and I did a little bit of the lithium borohydrides.
Okay. So do you have experience with this kind of experiments?
The inelastic neutron scattering, definitely.
Yes.
I've worked with people, Bill David, Bill David,
I know Bill
Jimmy
David,
Ramirez.
Yes, I
those
know
are the
him,
people.
I know Tim. Yes, we collaborate. We don't have official collaboration, but I do know him very well.
All right, I think we should continue.
Thank you.
Okay, so let's switch gear and go to some of the most recent work. So I've been working on lithium-ion batteries, or all kind of let's say with lithium-ion battery for the past few years. And so basically, so how lithium-ion battery works? I think this is basically during charging or discharging, where you see that there's lithium moving from, So you see there's oxidation and reduction, half reactions, giving rise to lithium plus an electron, and an electron will go through the external circuit here, while the lithiums, they will travel from the cathode to the anode and vice versa during charge and discharge, right? So this is basically how battery works. We have three major components, which is the cathode material and then the anode material, and in between is the electrolytes. And this electrolyte actually, facilitates, its only way that the lithium plus can travel from one electrode to the other. Now, what is the problem with present-day battery? So present day battery is just exactly like this. Most of the battery that they're based on lithium cobalt oxide and then graphite anode. So what happened is that, for the electrolyte we have today is lithium salt, mostly complex salt, that they are dissolved in high boiling points, high boiling solvent like carbonate and ethers. And because of this electrolyte, because you have all these, solvents, which is a carbonate. So sometimes during battery charging, if you have what we call thermal runaway, that gives rise to the battery heating up, as you can already observe for your cell phone sometimes or computer, then it's this organic solvents. We actually they are flammable, so they can combust, giving rise to this flammability and all these things. Sometimes also have evaporation and decomposition. So this is one of the problem with present day battery. Another is also there's limited energy density, and so this limited energy density is also somehow also related to the fact that we use liquid electrolytes here, so we cannot use high voltage, a certain type of electrodes that can give rise to higher energy density, if I should put it that way. So there is need for new battery chemistry, and that is where all solid-state batteries, or we call all solid-state battery, came into play, and it's a very big field. People are looking at, okay, can we find solid materials that can conduct ions, lithium or sodium, depending on the battery want, as fast as this ion can travel in this liquid, in this solution. And so that's why going from liquid to solid electrolyte, and with that we can actually make what we call all solid-state battery, whereby here we replace the graphite completely with with lithium metal, and then we can have other type of cathode material like sulfur, in the case of lithium sulfur battery. And with this, we can actually increase the energy density of today's battery by of 3, maybe, or more than that even. And then by doing that, we also should improve the safety. But then we have to find a solid material that is conductive. So surprisingly also, this complex hydride, in this case, so this is the complex anion. It can be bonded to either lithium or sodium or magnesium in any case. All these complex anion hydride, they also show high ionic conductivity. So here, we measure the conductivity of this material as a function of the inverse temperature, which means that the temperature is increasing as we go like this, right? So you can recognize these are all hydride-based material. What you see here, for example, if you pick this material, for example, you do see that at room temperature, the conductivity is very, very low, very low. And as soon as we begin to heat it around 110 degrees centigrade or close to 400 Kelvin, you do see that it undergoes phase transition, and then the conductivity is higher than 10 raised to power minus 3 Siemens per centimeter, which is what is required for a battery. So which means that actually at high temperature, all these materials, they have very impressive conductivity. And so I just try to show it more here. So what we do see here is that there's a phase change. This material go from the orthorhombic phase to the hexagonal phase, associated with significant increase in the ionic conductivity. And of course, because this is, it's an Arrhenius kind of behavior, because of certain, because of the energy you need to create a defect, which more defect can be created at high temperature. So most of this electrolyte only show high conductivity at high temperature. And I try to show here, basically, if you want to measure the ionic conductivity of a material, which is this a Q, is given by the concentration of the defect, because this material work based on defect. So if you have a crystal structure and then you have you have a defect, which in this case vacancy and interstitial site, then you have the hopping of this you have the hopping from here to here within the crystal structure, which gives rise to the fact that this ion can move. This is lithium plus, then it can move, into this vacant site, and then by doing that, you see there is basically ion mobility in your material. So it is based on the number of this defect that you have there, and then also the mobility of the ion carrier, which is, and then the activation energy, which is energy that you require to jump from one place to the other. So basically, this is what you need to understand. So if I want to increase the conductivity of my material, I can play with the activation energy, making sure I lower the activation energy to jump. And then also should be able to have high concentration of, the carrier, the charge carrier. So, so basically, this is just a simple introduction to this because we need to do it and understand this. So now our approach is also like, okay, well, can we also stabilize this high temperature phase? If you look at here, we do see that, okay, this is associated with phase transition. So can we stabilize this high pressure phase by nano confinement, which is our approach in this match? How do we do how to change the ionic conduction behavior? So why do we want to do that? So if you make a composite, there are three things that can happen. So we can have interaction at the interface, leading to what we call space charge formation, space charge layer, which can enhance, the different concentration at the interface, thereby leading to high ionic conductivity. So this is, you can see here the different concentration. And also we can actually stabilize some of these high temperature polymorphs at room temperature. And this is given by this Gibbs-Thompson equation. Basically, we can achieve very large depression or decrease in the phase transition temperature by playing with some parameter, which is like the radius of the material that we confine the hydride in, and then the interface energy between the interface energy of the hydride and the scaffold. And sometimes you can even form tertiary compound at the interface. So this is well known, and already also there's already some work that have been done on polymer related kind of material. So that is actually the idea of doing this. This is being shown also for example, the melting temperature for small gold nanoparticle. If you make gold very small, you can actually achieve significant decrease in the melting temperature of gold just by decreasing the size. The same thing here, the depression in freezing point of water. If you're able to confine water in silica, you can actually see that the freezing point will change by a large extent depending on the radius of the pore that you put your eyes in. And it all has to do with the radius here. It also has to do with the interface energy between your material and where you confine it. So this I don't know. So how do we make this nanocomposite? The same thing again we did before. Basically, you have your complex hydride in this case. You have either disordered pores or ordered one, and then you just find a way, you heat the sample, you melt it, infiltrate it, it infiltrates all the pores, filling all the small pores, or you can also do impregnation, but we prefer to do melt infiltration because it's much better. We don't have to deal with liquid in this case. So, and this is already something that I've already done to see that if you have, for example, lithium borohydride here, depicted here with, SBA15, this SBA15 is, highly ordered porous silica. You can tune the pores from 3 to even 16 nanometer. So if you put this material, you heat it up above the melting point of this LiBH4, it will melt, infiltrate all these pores of this material and stays inside the pore, as nano-confined material. And in this case, we needed to use oxide because we cannot use carbon. Carbon is very conductive. If you use carbon as your electrolyte, then you have conductive, electronic conductivity, which will result into short circuit. So we needed an insulator to do this. Okay. Now, so this is the first proof of point. The same lithium borohydride, which I've worked before as for hydrogen storage. Now, if you put it in silica, so what you see here is that, okay, this is the bulk-like. We have already seen this. So this is the phase transition happens here, associated with high conductivity. But in this case, if you put them inside these very small pores, what happens is that already at room temperature, the conductivity have about 3 orders of magnitude increase in the ionic conductivity at room temperature. So this works actually. And then we do know that at the interface, we have a very fast moving lithium ion. And then far from the interface, you have lithium ion that, the ones that doesn't move as fast as the other one. So if you're able to reduce this dimension, so the pore size of the silica of the scaffold, you can actually fill it all completely with very fast moving an electrolyte where you have very high conductivity of the lithium. And we demonstrated you can actually use that to make battery. I think this is one of the first also listed battery, lithium sulfur battery, based on lithium borohydride. So here we have lithium, and then we have lithium sulfide as our cathode, and then we can actually, do this reversible reaction. From here we have lithium sulfide. So this is lithium sulfur battery, really based on this lithium borohydride. You can see we can cycle it, of course, up to 40 times and now have better result. But it's just a first proof of principle that this actually works. And we have extended this research to many other type of oxide, and then you're also using them to realize even battery that can work at room temperature. And one thing that was also very remarkable is, okay, you can see also here different type of material all show this kind of behavior. But one thing I wanted to focus here is the fact that the nature of the scaffold has a significant impact on this increase in ionic conductivity. This is sodium imide, and this is sodium borohydride. Now, if I put my sodium imide in alumina, I have this increase in conductivity. If I put the sodium imide in silica, you see the increase in conductivity is much, much higher for silica. Now, if it is sodium borohydride, the only difference is just that the anion here is different. If I now put my sodium borohydride in silica, I just have very small increase in conductivity. But if I now put it in alumina, the increase in our conductivity is much, much, much higher. So it's a reverse case for sodium borohydride and sodium imide. And this is what we see for different kind of scaffolds, which means that there's a complex interplay between the property of the hydride and the oxide insulator. So we wanted to understand what is happening, why when you add this insulating material that does not have any form of ionic conductivity, you add them to an ionic conductor, you have orders of magnitude increase in the ionic conductivity. Why these are insulators? So it's the reverse that should be expected. So we wanted to understand this a bit more, right? So that is now we spend time really making nice, in-situ cell this time around to make sure, okay, that we don't have any oxygen leak, that what we can observe is what we have. So then we went to DESY to do this measurement. And then from DESY, we also went to ESRF first at ID20, where Christophe Saleh and Alexandro Longo actually works. And then we also went to DESY as well. We did this experiment with DESY. And actually, we spent 5 years trying to figure this out because we wanted to be sure that actually the result we get is not as a result of beam damage or any oxidation. That's why it took about 5 years for us to get this data. So I start from the lithium 1s edge here. So what did we do? We made composites that contains different amounts of the active material, which is LiBH4 in this case. Okay. So this is 130%. So in this case, we fill all the pores and we have extra of our lithium borohydride outside the pores to really give us interconnectivity so that we can really have connectivity, and then we have electrolyte that works. However, if you want to understand what happened at the interface, we have to make nanocomposite where we don't fill all the pores, so we can really tune, this interlayer distance so that we can actually probe most of the interlayer distance, the interface composition. Because in this case, you also have huge contribution from the bulk. So, and this is what you see here. If you start with this 130% pore filling where we fill everything, and we look at we compare the bulk lithium and then the nanocomposite, we do see, okay, there is a slight change, but we cannot conclude more. If you now just have about 50% pore filling, already you see there's an extra contribution here from the lithium, and then we do see that the concentration of the contribution of the bulk-like has actually reduced, and we now have some other features that we will talk about. But basically, by playing with the concentration, we can even go to even 30% or even a 15% pore filling, where you begin to actually see only the interface composition. So now we do the same thing for the boron. And this is even more remarkable. So the boron actually gives us even much better. So here we start also with the 130% porphyrin. And if you look at the bulk-like, lithium borohydride, in this case, you can see the bulk-like behavior. If you have 130%, you see that we have this small contribution of this, what we call, well, we saw before that look at oxidic boron. And then if you go to lower porphyrin, which is lower concentration, we do see that this bulk-like behavior is gone completely. So we do have this, only this particular thing. And then we can see also that this extended to TE. The transition region is also basically different as well. And of course, if you do fingerprinting, we try to do fingerprinting to figure out what is happening here, also combined with some calculations. But just to summarize, so we start with the tetragonal lithium borohydride. So this gives us the tetragonal lithium borohydride. And then we do know that this transition around this 194 is actually trigonal. And this trigonal boron is like LiBO2, BO2-3, and BF3 also, or BH3, or even BO3. So initially, when we did for the hydrogen storage, we thought, okay, we are forming lithium borates, which is also one of the referees actually concluded, which we knew it was not. But in this case, we are sure there is no oxidation. We did this experiment several times. But basically, what we do see that at the interface, we do have trigonal boron instead of tetragonal boron, which we think is something that looks like this, because it's not LiBO2, because LiBO2 is not conductive, neither is this conductive. Okay, so this is based on this fingerprinting. And we try to so what do I want to show here? We saw that the type of nanocomposite, so the behavior of this nanocomposite also depends on the type of oxide and the scaffold that we use. And if you don't focus on this, if you look at this, the boron, because the boron actually is much better. If we just compare this, we do see that the behavior, so this peak shift, that is different for this lithium borohydride that is confined in alumina. So this is same porphyrin as this one, that even the peak shift is actually different from the one that is confined in silica, which means that what we can conclude from this, comparing silica-based scaffold and alumina-based scaffold, is that the interaction at the interface is slightly different, because we can see also even for this that there are two contributions at a point. So this is what we can conclude from this. And I did mention this already before. If you even go to very low concentration of our sample, that is just 15% porphyrin, which is very, very close to interface, we do see also that actually you can see, so this is the bulk-like one, and then you see, of course, there's no signature of the bulk-like lithium borohydride. Rather, we can see this new peak, that is the trigonal boron. And when we compare the silica, this one is alumina and silica, you can see clear difference between these two. So we can see clear difference between these two in this case. So what we can conclude is that, okay, well, we have something that like something like BO bonds in the nanocomposites or tetragonal boron, but we can say that this is not completely oxidic boron, because LiBO2, like I mentioned before, is not conductive. And then, so we think that at the interface, we have something like this. So where we have this, because the surface of the metal oxide contains a lot of hydroxyl groups. So we think there's some kind of this interaction happening at the interface where the boron is close to the oxygen. And somehow this also affecting also the chemical environment of lithium, because we can see here that this environment, there's this other these things which look more like oxidic kind of lithium is quite different from the bulk-like material. So this is what we can we can conclude on this. We also did the same thing for the silica, for sodium borohydride and sodium-based material. We saw similar thing. We do see, okay, the appearance of this peak around 194 EV, which signify the tetragonal boron. And then we do see also, they're just concluding that actually the type of scaffold is different from silica. We do see that silica has different effect from alumina. If you look into this carefully, we see even where these peaks appear is different here. We have 194. In this case, we have 193.8. So slightly different for the alumina base and the silica based nanocomposite. And a very remarkable one is actually that here we look at sodium imide based composite, because the other one was, okay, we have something like BO-like bond, because, okay, there is boron there. So my expectation that if you also have something like NO bond for sodium imide base sample, then that will be conclusive that we really have interaction between the surface group of these materials and, you know, and our electrolyte, the active electrolyte material. And indeed, that is what we do observe when we compare different spectra, looking at different we did fingerprinting, looking at different boron-based kind of material and based on both sodium nitrate, especially comparing sodium nitrate or sodium nitrite with the peak that with all this peak we got, we do see actually that there is clear evidence of, you know, NO bond like, because we do see this kind of shift that suggests which look more like this. So we don't have, of course, lithium nitrate, but the comparison actually do show that actually there could be interaction between this nitrogen and oxygen on the surface of the silica and alumina, and the interaction is different for the different. You can see here, this is 179.7, and we do see actually that's just a conclusion that we do have differences between these scaffold materials. An interesting thing is then that, okay, if this interface composition, which we're still trying to figure out the exact composition, if this is actually true, then the concentration of this interface composition should scale with the conductivity of this material. And if we look at this, so we had a kind of model, kind of experiment where we have, we start with silica, and then we're able to cover the surface of the silica with alumina and then with zirconia. Why are we doing this? Because when you have pure silica or alumina or zirconia, then because they are chemically different, they have different surface area, and then they have different kind of surface properties. So if this surface area or pore volume or even pore size is the determining factor for the conductivity, then you are just comparing apple and oranges. So in this case, we try to keep the surface area the same. We only modify the surface with these materials. And indeed, we can see here that actually we can see that if we just use this as the active material, so this is the interface composition here, we can see that when we quantify the amount of this interface composition, that it scales with the conductivity we have. So this is the bulk-like ionic conductivity. If we now put this in just silica, this is what we have, and we can see here that it has less composition. If we put it we put it here in aluminum modified silica, we can see we have more of this tetragonal boron-like material. And then when we now put it on silica that is modified with zirconia, the same amount, the same surface area, we do see that the concentration of this interface, the interface composition is much higher here. And then the conductivity is also high in this case. And if you want to know more, we just published this work recently in Advanced Energy Material and also in Small Methods, where we summarize this finding. So what does it lead us to? So we do see here, what can we learn from this? We do see here actually that then modifying the surface actually is key. And why is it? Because if you, for example, if you take like silica, for example, we do know that the silica has a lot of surface groups, different kind of, OH groups on the surface. Some are basic, some are acidic, especially for alumina. In terms of silica, it's only really basic. We have in some of silica, we do have a lot of this surface group. And in terms of alumina, we can have really also acidic groups and basic group. But also alumina is quite different because you can also have even Lewis acidity. I think that's the point I'm trying to make. You can have Lewis acidity on that. If you also look at carbon, the same thing. Carbon is always covered with a lot of surface groups. here. So even for the carbon that we used before, so those like BO-like bond that we saw would just be interaction between the LiBH4 and this surface group, leading to something just at the interface that looked like boron BO, which means that our sample was not completely oxidized as we thought those days. It's just the fact that the surface groups that our active material interact with these surface groups actually to give us the X-ray pattern that we saw. So, and this is basically what we think that is happening. So we have this the silica surface or any of the oxide surface, and then when we add, you know, lithium borohydride or any of our active material there, electrolytes, there's some kind of interface reaction that gives rise to, you know, either this or this. We are still trying to probe exactly the exact composition of this interface composition, the exact phase that is giving rise to this high ionic conductivity. But what we do know and we do think is that it's highly defective. And because of the fact that it's highly defective, so you have a lot of, the defect concentration is very, very high, that actually we have high ionic conductivity in these materials. So the surface interaction matters actually. So, and then with this, we now, this I think about the last slide. So we say, okay, well, if the surface interaction matters, we know that we can tune this surface interaction. So we can really modify our surface. So here we just use this lithium borohydride. So we confine them in different SBA 15. This is 6 nanometer. And then this one is about 10 nanometer. So you can see already the pore size, the fact that the pore size is different, give rise to different conductivity. So what do? We know that if you dry this oxide at different temperature, we can actually change the density of the surface groups. So you can see here, you know, that the density of the surface group changes by just drying at different temperature. And this is what we did by drying. So we have the vacuum, just vacuum dried. We dried at 100 degrees centigrade, 200. So what we do see is that if you don't dry the material, the conductivity is low. So this is the conductivity is low. Simply because you have a lot of water there, and this water is going to react with our lithium borohydride or the electrolytes, giving rise to something that is not conductive. So if you remove the physics of water and have only the surface OH groups, so which is around 300 degrees centigrade, you see that your conductivity is maximum there. If you now begin to dry the silica more, then what happens is that you have condensation of the silanol group, so you have less amount of silanol group in the surface. And then what you see is then that because we're removing so much of the silanol group, so this amount of silanol group that we remove so much of silanol group, then we do see that the conductivity decreases because our active material don't have enough surface group with which it can interact. So this is just consequence of our understanding from this X-ray Raman scattering. And what we can even do is to completely modify the surface group, So we can remove this silanol by just doing something we call, you know, methyl modification, selenation, and we remove all the surface groups, and we can even have super, very hydrophobic silica surface. And when we did that, you can see that actually we go from this high conductivity, the highest here, to very, very low conductivity here. And actually, I don't have time to explain why, but actually, in fact, we're able to have this, even this conductivity, which is lower because of the fact that we are not able to completely remove all the silanol group. There's some we call the, you know, the isolated silanol groups that are, you know, cannot penetrate to remove. So we think there's just this isolated silanol groups that is still responsible for this enhanced in conductivity in this one, but it shows the lowest conductivity when we remove most of the silanol groups. So, so the interaction matters. So I think basically this is bringing me to the conclusion. So I hope I have convinced you that actually complex or metal hydrides in general, especially the nanocomposite material, they are very promising class of energy materials. So reversible hydrogen storage, I show solid-state electrolyte for batteries, also hydride ion conductor. Actually, I have some result I'm not showing here. We see very high mobility of the hydride in these materials, you know, and also for catalysis, I didn't show a lot of here. So basically interface effects, you know, especially interface formation, play a crucial role in their hydrogen, not only in their hydrogen sorption kinetics and also ionic conductivity. Also in battery application, I didn't show actually how this changing, making this nanocomposite also even leads to better battery performance. So the exact composition of the interface is quite complex. It's highly, a highly defective phase. So it's trying to use a computational model to really begin to figure out what is the exact composition that is actually giving rise to this improved performance of our material. So then if you change the scaffold, we can fundamentally tune this interface effect, and then that means we can actually tune the performance of our metal hydride, either for ionic conductivity in batteries or for as a solid state electrolyte, or even for catalysis, which I didn't show here. Really tuning this interface interaction is key to actually rationally designing new nanocomposite material with improved performance. And I want to thank the following people here who all have contributed in this work one way or the other to this work. And also the funding agencies, my funding agencies, and also the collaboration with this ESRF and DESI, the beamline scientists there played a major role, and you all. And also this is the materials chemistry and catalysis is quite a large group, and then we have 5 PIs, and each focusing on certain area of material related to catalysis, heterogeneous catalysis, advanced spectroscopy. I think that's where, so Frank De Kroog is also my colleague. So advanced spectroscopy, but also TEM and real fundamental of catalyst preparation. And with this, I am done. Thank you for listening.
Wonderful talk. Thank you so much, Peter. Given the hour, I'm going to stop the recording.